Okay, let's begin. So here's where we were. We've seen that neural networks are function approximators. They can approximate any function. We typically make them approximate a specific function by adjusting the parameters of the network. Can you shut your laptop? All of you guys, okay? And we do so in a manner that minimizes the expected error between the output of the network and the desired function, except that you don't actually know the desired function everywhere. So instead, we minimize the error at a collection, the average error over a collection of training points. That gives us a loss function. And the loss function, if I can figure out how to, somewhere here is a pointer, I think. Can you see a pointer? Not the mouse, but the crazy. There's supposed to be a laser pointer here. Can you see one? Doesn't seem to be doing, it's very faint. All right, so anyway, and so we define the loss function, which is the average divergence over the collection of training points. And this we know is just a function of the weights of the network, the parameters of the network. And this is what we will minimize. This is a problem of function optimization or minimization. Now, we saw that we would be doing this through gradient descent in the last class. So the question now is, how do we compute these gradients, and what are these gradients? So first, some notation. I'm going to be representing things in this manner. The network variables are all called weights, including the biases, unless I explicitly denote the biases. So if you see something such as this, W subscript ij superscript 4, it means it's the weight of the connection from the ith neuron in the third layer to the jth neuron in the fourth layer. If you see B subscript j superscript 3, it means it's the bias to the jth neuron in the third layer. All the net neuron outputs are labeled Y. The subscript represents which neuron it is. And the output, of course, doesn't have a superscript. If the Y has a superscript, it represents the layer number. And here's how we are going to be doing the gradient descent. As we saw earlier, you initialize your parameters. And if the loss has not actually converged, at each step, you update your parameters against the gradient of the loss with respect to the parameters. By the way, guys, I expect people in class from the next class, not watching over Zoom. If you're signed into the in-class section, what you have done is to prevent people from signing in. And so if you're not here and if you're in class, then I will mark you absent, okay? Because your presence in class comes at the cost of somebody else. Okay, so here's the overall neural network class. This is what we are trying to find the gradient of with respect to network parameters. It's the average of the divergence over all training points, right? And of course, once we define the loss, when we are using gradient descent, this simple rule breaks down to this. Every single parameter is going to be adjusted against the partial derivative of the loss with respect to that parameter. And now this makes complete sense. What does this term derivative over here mean? D loss over dw. What does it tell you? What does it tell you? Yeah.
The direction of maximum set in the direction of ID.
So basically, d loss over dw tells you how much the loss will change if you perturb w a little bit. So if it's positive, then it means that increasing w is going to increase the loss. If it's negative, increasing w is going to decrease the loss. So at each step, you're going to adjust the weight against the derivative. Moreover, the magnitude tells you how much the loss will change. So it makes sense. You're going to perturb each parameter in a manner that locally reduces the loss. That's all we are doing. It's a very simple, intuitive algorithm. Make sense? Right. But then the key term over here is the derivative of the loss with respect to these parameters. And the loss is the average divergence over all training points using the linearity of derivatives. So this is going to be the derivative of the loss is going to be the average of the derivatives of the divergence with respect to the parameters, which means this is the term. This is the term that we have to figure out how to compute. What is the derivative of the divergence with respect for any given input? There is an output. There's a divergence between the output of the network and the true and the desired output. And we must figure out what the derivative of the divergence is with respect to each of the network parameters. So before we do that, we're going to go through a quick calculus refresher. Now, for any differentiable function x, y equals f of x, if it's a scalar x and a scalar y, we know we can write y equals, the derivative is written as dy over dx, or partial y over partial x. And what does this derivative mean? This derivative represents the multiplicative factor with which you must multiply a small increment in x to compute the corresponding increment in y. You all remember this, right? Nothing new. I can represent this using a little picture, assuming I can find myself a chalk. So the figure, the notation is as follows. When I write y equals f of x, then what we are saying is that x influences y. Changing x will change y, right? And specifically, the manner in which it influences it, I'm going to represent this using the derivative of y with respect to x. So when you write it in this manner, then you can say x influences y. And moreover, now this means that any perturbation x is going to result in a perturbation y. And this is a standard graph notation, which tells you that delta y equals dy over dx times delta x. Is this representation making sense to you guys? This little influence picture that I've just drawn. Good for all of you? You guys at the back, yes?
Or the second diagram, when we define dy by dx with shape, that a small change in y will result in a small change in x.
Correct. Small change in x will result in a small change in y.
But now that we're saying that a change in y is a small dy by dx over a small change in x. I'm not able to understand the essence of that. Could you just tell that again, sir?
So this is what we are saying, right? The derivative is the amount by which you must multiply the increment in x to get the corresponding increment in y. You remember we explained this? Yeah, that's all we are saying. I'm representing this as a diagram in this manner. So when I say x influences y, that means any small perturbation of x is going to result in a perturbation of y, and the corresponding relationship is given by delta y equals the derivative times delta x. So now suppose I have a function of this kind. Y is a function of many x's. What would the influence diagram look like?
Dy by dx 1 times x1.
What will the influence diagram look like? Anybody? Yeah.
Delta x1, delta x2, delta x3 all have their own arrows.
So again, this is the basic influence, right? What are the variables influencing y?
x1, x2, x3.
So it's going to be x1 through xn. Each of them is going to be influencing y. Is this making sense? Right? And then what are the edges? What weights will do you mind shutting your laptop? Please. I don't mind you opening your laptop. Just go outside, do your work, and come back. Okay? So what weight will the edges carry? Yes? The partial derivatives of y with respect to x. xi. And now, what will delta y be? Anyone?
Summation of the weights into
It's going to be the total contribution over all the edges, correct? And so then I can say this is going to be summation over I delta xi times dy over dxi, written in any order. Is this making sense? This is basically this influence diagram, and we're going to use this a little bit in class. And so that's what this thing is going to look like, this particular influence diagram. Everyone with me? Okay, so now once you figure this out, you can actually see other things. So which is why you can see, delta y equals the partial of y with respect to x1 times delta x1 plus the partial of y with respect to x2 times delta x2 and so on. Yeah.
How did you write units before
Delta xi before. These are scalars in this example, but yeah, the order is important. Thank you for pointing this out. We'll get to this later in class. Okay, so is everybody cool with this picture? So now suppose I have y equals f of g of x. This is a nested function, right? If I have a nested function of this kind, then clearly I can draw the influence picture and the influence diagram in this manner. I can say x influences, say, g, because g is computed from x, and g in turn influences y. What will the edge weights be? Anybody? Yeah. So dg over dx, and this is going to be dy over dg, right? And then if you work this out, delta y is going to be dy over dg times delta x. That's what the figure is telling you, right? And what is delta g? Sorry, this dg, right? Don't just nod when I'm making mistakes. It means that you're not paying attention, right? And what is delta g? So delta g is going to be dg over dx times delta x, right? Which implies delta y equals dy over dg times delta g, but then I can just plug in this formula for delta g. And so that's going to be dg over dx times delta x. So this gives you this famous chain rule, which tells you how nesting happens, the derivatives of nested functions. Everybody with me? Including those at the back? Okay. So that's why you get this very simple chain rule. Now I can take this one step further, and I can have a function of this kind, where y is a function of many variables, but each of those variables is in turn a function of x. What would this influence picture look like? Anyone? Mm-hmm.
It's like a diamond.
It's like a diamond. This is going to be a diamond. Thank you. X will influence each of these. Let me just say zi equals gi of x just for ease of notation, right? So x is going to influence z1 through zn, and each of these is going to influence y. Correct? So now, based on this, what are the edge weights? What are the edge weights?
dz by dx.
This is going to be dzi over dx, and this is going to be dy over dzi. So if you just combine these, what is the derivative of y with respect to x? Again, y depends on all of these z's, right? So I can say dy delta y equals summation over I dy over dzi times delta zi. Correct? And delta zi in turn equals dzi over dx times delta x. So this gives you your distributed chain rule. Everybody see how that figure worked? We will use it. These pictures are very nice. When you actually begin drawing these pictures, it makes all kinds of computation of derivatives trivial. Things that you thought were very complicated in high school, if you draw these pictures out, you'll find out that they're very trivially derived. And so that's, in this case, this one is easily obtained, right? Okay. So, which gives you the equation for the partial derivatives. Any questions? No. Okay. So now our problem for today. How do I compute the derivative of the divergence with respect to the weights, an individual weight in the network? So, but first, to Paul. Tell me. I managed to mess up this board. I'm going to erase this. Okay, time's up, guys. Can someone on Zoom tell me the answer to the first question? Zoom, true or false? Anybody on Zoom?
True.
True.
It is.
Okay.
True.
And the second one, is the first statement true?
Yes.
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 Second?
No.
Yes. True as well.
All are true, correct? So beautiful. Now, so let's go back and compute our derivatives. I'm going to use this simple toy network just for purposes of illustration, but then, yeah. This is, everything here will be generalized, right? Now, do you mind shutting your laptop? Seriously, don't open it, right? Unless I let you ask you to do so. You too, Mark. Thank you. Now, so within each neuron, remember that there are two operations happening. The first operation is that we compute an affine function of all of the inputs. So you compute an affine value. And then the second operation is that we apply an activation to these affine values. That's what happened inside each perceptron. So if I write down all of the variables using the notation we had earlier, here are all the weights. In this particular representation, I've also called the bias a weight, but you could also notate them separately. But then you have other variables computed. Within each neuron, first you have an affine value z computed. So the notation z subscript I superscript something means it's the ith, so z subscript I superscript j, or more generally, let's consider this, z subscript 1 superscript 2 means that it is the affine value for the first neuron in the second layer. The superscript represents the layer, the subscript represents the neuron number. So also, this is what goes into the activation. And so the output of the activations is being represented using y. Again, same notation, the subscript represents the index of the neuron and the superscript represents the layer, okay? So now the network eventually produces an output y, which is compared against a desired output d through a divergence function. And we have to figure out what is the derivative of the divergence function with respect to any individual weight. And so observe how this happens. If I want to compute the derivative of the divergence with respect to, say, this weight, the question I'm asking myself is how much will a small perturbation of W out here perturb this divergence out here? So I have to follow the influences a long way down, right? Now, the way I will do it is to figure out how much does a small perturbation of this guy influence this guy. But this small perturbation, how much does that influence this one and everything else downstream? And how much do these perturbations influence this? And how much do these perturbations influence this? You have to follow the chain all the way to the end to figure out how much a small perturbation of W is going to perturb the final divergence, right? And you have to follow all the influences going from the beginning to the end. And for this, we know that, sorry, if I want to find out how much a perturbation of z influences y, this derivative depends on the value of z, because these functions have varying derivative with the input, right? And so this means we need to know the value of z. So before you can compute the derivative of the divergence with respect to a w way out in the beginning, we need to compute all of these intermediate values so that we can figure out where to compute the derivative. And this is going to be computed first using something called a forward pass. So in order to compute the derivative of the divergence with respect to the network parameters for any given input x, the first thing we will do is to pass the input x through the network to compute all the intermediate values. And this is easy enough. So just for sake of notation, I'm going to call the input x y superscript 0. So y superscript 1 was the first layer. The 0th layer value is simply the input, right? And so again, I don't have an explicit bias in my notation, but you can always work this out. This is only for illustrative purposes. What we will do going forward is we present the input, and then the very first thing we are going to do is to compute the affine value at these input neurons. The affine value is simply going to be the weighted sum of all of the inputs, right? And the weights are going to depend on the neuron. So you can compute this affine value for all of the neurons in the first layer. The formula itself is trivial. It's just going to be the weighted sum of the inputs where the weights for the jth neuron are specific to the neuron itself. So I'm using wij to get zj, right? And once I've computed all of these values, I can apply the activations in that layer and obtain the corresponding y values going forward. Then I can use those y values and compute the affine values at the next layer. And again, the formula is very trivial, right? It's just the weighted sum of all of the y's from the previous layer to compute the z's. And then I can apply the next set of activations and follow this computation through the network all the way to the end of the network. So the very simple pseudocode for the forward operation, it's very trivial. I'm assuming that yi0, superscript 0 is the input. Then you're going to go through the layers from 1 till the nth, what is this iterator? We're going to go through the layers 1 through n. Within each layer, you're going forward. This iterate is going forward. Within each layer, you're going to go over all the neurons in the layer. And for each neuron, you're first going to compute the z value, which is the weighted sum of the outputs of the previous layer. And then once you compute the z value, you're going to put that through an activation function for that layer, and you get the output y for that layer. This you can follow all the way to the end of the network. Is this clear to everybody? It's not complicated, so I don't have to go through this, do I? And so pseudocode, for those who prefer to see it in terms of code. It's in the slides. I'll just move on, okay? And now, having performed the forward pass, you would have computed the output around here at the output of the network. And from that, you can compute the divergence, which quantifies the error between the actual output of the network and the desired output of the network. Now observe how we computed, how we said we needed to compute the derivatives, right? If I want to compute the derivatives, I have to figure out how much does a small perturbation of this influence this, how much does a small perturbation of this influence this, but you can't go forward. For that, you would have to work your way backwards. You know where you are. So the first thing you have to do is to say, how much does a small perturbation of this y affect the output divergence? Having computed that, then you'd have to take a step back and say, how much does a small perturbation of these z's influence the divergence? And now it's going to be a two-step forward, a two-step thing, because you need to know how much does a small perturbation of z influence y, and how much does a small perturbation of y influence the divergence. That's why you have to go backwards, because if you want to compute how much a small perturbation of this influences the divergence, you already need to know how much a small perturbation of y influences the divergence. So you can't go forward because there would be missing terms. You have to go backwards when you compute these derivatives. That makes sense to everybody, right? And so from this, you'll be computing the derivatives for these weights, then go back and compute the derivatives for these y's, for these z's, for these weights, and so on, all the way till the beginning of the network. Any questions? Okay, so let's see the math. so long as you understand how we are going to do this. First, we said that the divergence function is something that we design. So we're going to assume that based on our design, we know how to compute the derivative of the divergence with respect to the inputs to the divergence function. This would depend on the divergence function. If this was an L2 divergence, you're going to get something. If it's a KL divergence, it's going to be something else. It depends on the specific divergence function that you choose, right? So let's assume that I have the partial derivatives of the divergence with respect to the output of the network. Then I can use this chain rule, right? If I have y equals L equals f of y, where y equals g of z, so L is my loss. My loss is some function of the output of the network, but the output of the network is some function of z. So chaining them, the derivative of the loss with respect to z is going to be the derivative of the loss with respect to y times the derivative of y with respect to z. Make sense to everybody? Right. And so that's easy. I can just say the derivative of the divergence with respect to each of these z's is going to be the derivative of the divergence with respect to this y times the derivative of the y with respect to z. And what is the derivative of y with respect to z? That's simply the derivative of the activation function, right? And so this term, the derivative of the divergence with respect to y, is already known at this point. This guy here is simply the derivative of the divergence with respect of the activation function. And so combining the two, I now have the derivative of which is computed at a specific location, which was computed in the forward pass. And so putting them all together, I have the derivative of the divergence with respect to these z's. Any questions? This is absolutely trivial, is it not? Okay. So then I can take a step back. Now I can say, what is the derivative of my divergence with respect to this weight? And using the same chain rule, the derivative of the divergence with respect to this weight is going to be the derivative of the divergence with respect to z times the derivative of z with respect to the weight. And what was the relationship we had? For any given weight wij, we had zj equals summation I wij, I can call this wij by I plus summation k not equal to I wkj yj, right? So I'm just saying that if I want the derivative with any respect to any particular weight, I just pull the contribution of that particular term out of the summation. So if I do this, what is the derivative of zj with respect to wij? That's simply going to be yi. Correct? Everybody with me? Nothing fancy, right? So the derivative of this z with respect to this weight is simply going to be the term at this node. And so this derivative of the divergence with respect to z was already computed as you were going back. The derivative of z with respect to w is simply going to be the y out here. I can plug that in. And so I have my derivative of the divergence with respect to that weight. This is something that I'm going to need for the gradient update rule, right? Gradient descent. Everybody with me? Yes.
According to the chain rule, the two terms in that expression, like on the right side, shouldn't they be flipped, or are they in this order because of the?
These are scalars.
Sorry.
These are scalars. Does it matter?
Oh yeah. Okay.
Right? So I can be careless. But when I'm writing matrices and vectors, I have to be a lot more careful. We'll get to that. Right? Okay. I'm speaking of the individual weights. And so now I can use this to compute the derivatives for all of these weights. The next thing I want to do is to go back and compute the derivatives for the y's, right? And the derivatives for these y's, for this, I'm going to need the distributed chain rule. Again, we just saw this, right? Now, if you go back and look at this y influences both of these z's. And both of these z's, in turn, eventually influence the divergence. Correct? So if I want to compute the derivative of the divergence with respect to y, I'm going to have to sum over all, just using the same principle here. I'm going to have to sum over both of these z's. And the derivative of the divergence with respect to y is going to be the derivative of the divergence with respect to this z times the derivative of this z with respect to y, plus the derivative of the divergence with respect to this z times the derivative of the z with respect to y. Everyone with me? Nothing fancy, right? It's fairly straightforward. And so again, the derivative of the divergence with respect to z was already computed. This guy, using the same principle out here, the derivative of zj with respect to yi is simply going to be wij. And I can plug that in. And so now I can compute the derivatives for all of the y's in this layer using the same formula. Any questions? Any questions? What would the next step be? What would I compute next? Anyone?
Derivative of, you'll have to find the derivative of y n minus 1 with respect to z n minus 1.
That's part of it, yes. But what is the overall computation? Yes. You're going to be computing the derivative of the divergence with respect to all of these z's, correct? And that is going to need, that's going to be the derivative of the divergence with respect to these y's times the derivative of the activation function. And then once you have that, what is the next thing you'd compute? Anyone? Yeah. Yashwani? Right here, yes. Wait, no, z of n minus 2 or y of n minus 2? What else would you compute? The derivative of the divergence with respect to these weights. This is what we're trying to compute, right? And then you can go back and compute the derivatives with respect to the y's. And then you can keep following the same rules going backward all the way to the beginning of time. In fact, you can even compute the derivative of the divergence with respect to the inputs. And that will tell you how much perturbing the input a little bit is going to change the divergence of the loss, right? So everybody with me? Beautiful. So this was easy. So here's a little bit of pseudocode. You would initially compute the derivative of the divergence with respect to these y's. Then you keep going backward. And here's the lovely thing. If you look at how you go backward, at each point, the first thing you compute is a weighted sum of the derivatives immediately following. And then you're going to pass these derivatives with respect to y backward through the activation. Does this look familiar? This has the same structure as the forward pass, right? What did we do in the forward pass? We first computed a weighted sum of all the inputs, and then passed it through an activation, right? In the backward pass, you're computing a weighted sum of all the derivatives at the output, and then passing it backward through the activation. In fact, the same code that you use for the forward pass can be used for the backward pass if you use a different set of variables. Make sense? Right? It's that simple. And so if I were to write this out, I'm going to go down, and of course, at each point, you're also going to take one extra step, which you don't have in the forward pass, which is computing the derivative of the divergence with respect to the weights. So if I write the whole thing in pseudocode, this is what it's going to look like. I'd initially compute the derivative of the divergence with respect to the outputs of the network, because that is distinct from all the rest of the operations, from which, of course, I could compute the derivatives of the divergence with respect to the affine values at the output layer and the weights of the output layer. I'm just putting them out because they tend to be somewhat separate from the rest of the network. And then subsequently, if you look at this, at each point, this looks a whole lot like the forward pass, a backward weighted combination of the derivatives of the next layer, and then taking a step back. This is the backward step of equivalent of an activation. Instead of passing it through the activation, you're passing it through the derivative of the activation and multiplying. The analogy visible to everybody? Questions on Zoom? Any questions? Okay. So this actually looks just like the forward pass for those of you who aren't paying attention. Okay, time's up. So, can someone from the back, am I allowed to invoke one of you guys? All right, you guys don't have your name tags out. So what's your name? Pardon me? Tony, okay. What is the answer? The first one. Tony says the first one is true. Is that correct? No, okay. Somebody else. What's your name? Aiden. Okay, Aiden, what's the answer?
Third one.
The third one. Right? Backpropagation is not the process of training the network. What is backpropagation the process of?
Finding the derivative.
Backpropagation is this business that we just saw. It's the process of transferring derivatives slowly backwards through the network to compute derivatives. Backpropagation is the process of computing derivatives. It is not used to update model parameters. What is it being used for? It's just used to compute the derivative of the divergence, right? And so the backprop is used to compute the derivatives of the divergence with respect to model parameters to be used in gradient descent tuning. Do you agree with that? Okay, Aiden, what about you? Sure, okay. All right. Pay attention, guys. I know it's easy for you to zone out. It's easy for me to zone out. You're just listening. I'm blathering for 80 minutes. Spare me a thought, right? Okay. So special cases. So far, we have assumed that the computation of the output of one neuron does not directly affect the outputs of the other neurons. Can you think of some things that we have seen where this is not true? Softmax, computing the output of one at one point affects all the others because they must all sum to one, right? So you can have various things. There are various variants that we've actually got on the slides. Please look them up. They may appear in the quiz, but I'm going to go through some of them, right? The first one is vector activations. In the scalar case, you had activations of this kind where the activation applied individually to all of the z's, to each of the z's. But in the vector case, we saw a generic function where the function was of the nature where if I change this z, that y might change. So the second case can be thought of as a generalization of the first case, right? And so in the first case, I can just think of each y as being a function of the corresponding z. In the second case, the way I want to think about it, I want to say this entire column of y's, which I'm representing as a vector, is actually a function of the entire column of z's. And modifying any z can change any y. Does this make sense? Okay. So when I'm computing my derivatives backwards, here's what the influence looks like. In the scalar case, each z influences only one y. In the vector case, each z potentially influences every y. So in this case, how will the backpropagation rules change? Anybody? Someone want to take a guess?
Partial derivative will include the other inputs as well.
The partial derivative is going to include the other inputs as well, right? For the scalar case, I said d div over dz was simply d div over dy times dy over dz, right? In the vector case, the z influences every one of the y's. And all of those y's eventually can influence the divergence. So the derivative of the divergence with respect to any z has to sum over all y's. And it's going to be the derivative of the divergence with respect to each of these y's times the derivative of the y with respect to z summed over all the y's. Make sense to everyone? Special case, the softmax, right? The softmax was this. Each of the z's was exponentiated, and then the exponentiated z's were normalized to sum to 1. So they look like probabilities. Now, we already saw in the last class this had a specific effect on the derivatives. And what was the effect on the derivatives? If I had a bunch of z's, z1 through zn, and the corresponding y1 through yn, what was the sign of the derivative of any z with respect to any y with respect to the corresponding z? Positive y. Why? Why? Yes.
Because increasing the corresponding z would cause an increase in the y, which for a different one, it'd be negative.
Make sense to everybody? Right. Okay. So what was the derivative of any z with respect to any y with respect to one of the other z's? Why? Why?
That z wasn't in the numerator.
Increasing this z is going to increase this y. So it must decrease the rest because they all sum to 1. Everybody remember that? Okay. And the actual formulae, again, you're going to have to sum over all of these guys. And if you look at the formulae, look at this. The derivative of y with respect to any z is simply going to be y times 1 minus y. You'll observe that it's always positive, right? And it also has a very satisfying behavior. Meaning if y is already close to 1, can you change it a lot? No, right? Can you change it a lot in the positive direction? No. So, so what will the derivative be? Is it going to be large or small? Small. So you have a y times 1 minus y. Similarly, if y is very close to 0, can you push it? Can you change it a lot going backwards? No. So what will the derivative be? Magnitude. Small also, right? So y times 1 minus y also satisfies that. Intuitively, does that make sense? When does y change most? In the middle at 0.5. At 0.5 is when you have the largest derivative. So you don't even have to work the arithmetic out. If you just think about it, this makes sense. Does it not? Right? If you think about it in terms of the behavior of derivatives, all of these things make sense. It turns out that a lot of math doesn't need symbols. It just needs visuals and thinking, right? Similarly, now the derivative with respect to any of the other y's. If I want to look at the derivative of this y with respect to this z, then if this y is already large, is there any room for, or let's say if this y is already large, is there much room for changing? You want to decrease it, right? So it actually ends up that what you will find is that this thing is going to be greatest when y's are 0.5 because the y's sum to 1, right? And because you're using two different y's, you're going to be using y, the product of the two y's. And again, this is going to change fastest when the thing is very confused and all the y's are equal. It's going to change slowest when it's very certain about one of the y's. That makes sense again. And this is what we're going to use, right? So there are other kinds of special cases on the slides, but then there's something I like to, two special cases that I like to emphasize. One is the ReLU, right? If I look at the ReLU, eventually I have a z that goes into an activation function. And the activation function is y equals z when z is positive, y equals 0 when z is negative. So when z is positive, what is the derivative? You guys, when z is negative, what's the derivative? 0, right? At z equals 0, what is the derivative? It's not defined, right? So we have this situation where if I have something like this, then if I look at the derivative, here it is 1, here it is 0. What about at this point? Now at this point, there is no derivative, but for our purposes, there is some useful information here. What were we using the derivative for? Specifically? You're going to say if a small, how much does a small change in the input change the output? Correct? So how much does a small change in the input change the output over here? How much does a small change in the input change the output? Anybody? Okay. So you there, the one who's sleeping, the one who just turned back, that's you. Yes. Okay. How much does a small change in the input change the output?
Not sure. What do you mean by n?
This y equals f of z. It's, it's ReLU of z, right?
Yeah.
That is, z is the input, is it not?
Yeah.
So how much is a small perturbation of z? Change y at 0.
Would it be dy dz?
I'm not asking for the formula, I'm asking for a value.
I guess 0.
Is it 0? Depends on the perturbation, correct? If I perturb it this way, then delta y equals 0, right? If I perturb it this way, delta y equals 1. That make sense? So I can literally say, yeah, delta y equals delta z, sorry. So I can literally say that the perturbation lies between 0 and delta z. And one way to think about it is that, I'll see if I can get this to work. You can think of the line as changing. Why can't I see this? I mean, I could stop the line at 45, so it went all the way to 90. But you can think of the line as instantaneously rotating from 0 to 45, right? Which means that every one of those slopes is valid at that point. That makes sense to you guys? You can use pretty much any slope between 0 and 45 because you can think of the line as instantaneously rotating, right? That's an arbitrarily precise approximation. And so you can use any derivative between 0 and 1 as the derivative at that point. Typically, you will use 1 because you want the network parameters to change fast. Did that make sense? So this is a specific example of what is called subgradient descent. But if you think of the function as changing instantaneously but continuously, you get the range of derivatives that you can use at that point validly in a gradient descent rule. Any questions? Including you. No, okay. Sorry, what's your name?
Ayush.
Ayush, sorry. I don't mean to harass you. I just keep everybody awake in class, okay? So everyone with me so far? So we typically use 1, but if you want to be very conservative and don't want to change the parameters too much, then you'll use something else, right? Slowly, yeah. Thank you. So here's another one. This is actually another instance of a ReLU, but we'd like to think of it differently. So y equals max of, say, x1, x2, x3, and so on. Suppose I have a max function, and specifically, let's say it has x2 is the largest value, right? What is the derivative of y with respect to x1? Does perturbing x1 change y? Yes. Depends? I'm saying x2 is the largest value, right?
But if you put x1,
By how much? If it's small enough, if the two are distinct enough values, then there's always a perturbation smaller than the difference, right? What is the question?
In practice, do we ever use like a partial value between 0 and 1 instead of
Almost never. I'm not actually, but it's still, but there are not in this case. There are other situations where one does.
Okay. Would
Right?
it not be? Is there not say like a advantage to say when you're starting off you want to have very high changes in your network, so you use a value of 1 and 0, but then say as you get closer, as you have trained for longer, so like scale based on the number of epochs or something, then you want your model parameters to change less. So
It makes sense to say that, but when your model is working properly, the odds that you'll end up at that corner are very small, right? So in this case, the derivative of y with respect to x is going to be 0 with respect to all of these guys. What is the derivative of y with respect to this largest value? 1, because perturbing it by a little bit will also perturb y correspondingly. What happens if you have two x's which are the same value? What will you have? The discontinuity, but then what can you say, right? Anything between 0 and 1 is valid for both of them. It's the same thing, right? If you perturb 1 the other way, the derivative is 0. If you perturb it one way, in one way it's 0, in the other way it's 1. So you can choose anything between 0 and 1 for both of them. That make sense? Yeah.
Even if you say anything between 0 and 1 is valid for both of them, either of them has to be 1, right?
No. That's independently computed, right? Yeah. So fantastic. You guys are on top of things, right? Here's a poll. Okay. So that correct answers.
Z3 is 1 and the 2 are 0.
Okay, so Z3 is 1 and the other 2 are 0, right? Everybody's with me on this one. Easy. So you get the idea. And so when you're doing a backward pass, so when we are trying to update the network, we have a forward pass which computes all the intermediate values, and then a backward pass going back through the network, where we saw all of the various derivatives being used at various locations. In some cases, when you have funky functions like maxes and ReLUs, and if you happen to be at a corner, then the terms that we would use are what we call subgradients or subderivatives. Now, the term doesn't always hold for all functions, but we generally call it subgradients. And again, the idea is to think of it as a function that's changing instantaneously from one value to the other, right? Now, so the overall approach for each data instance, pass the instance forward through the network, store all intermediate outputs, then sweep back through the network, iteratively compute all derivatives with respect to weights. The actual loss is the average of the divergence over all training instances. And then the derivative is the what backprop does is to compute this term, the derivative of the divergence with respect to network parameters for an individual training instance. You would have to do this over all of your training instances, average these derivatives, and that is going to be the derivative of the loss with respect to the network parameters. This is what you would use in your gradient update, right? Any questions?
What do you mean by actual loss?
The loss is, the loss is the average over all training instances, right?
Yeah, approximating.
The loss is how we define it. The term that we wanted to minimize was the expected value, but the loss we minimize is the average error over all training instances. That's the empirical error. So when I speak of actual loss, I'm speaking of just the empirical error over here. That's all. I mean, it gets confusing, but you guys are with me, right? Everybody's with me. And so here's the whole training by backprop process. I'm going to go over all of my training instances, pass each training instance through the network, yes.
In the previous slide, I just wanted to confirm that the loss is transposed because the loss of the derivative, and in gradient descent, we want the gradient.
Yeah, this is, there's a transpose here, yeah, because the derivative is transposed. Yeah. That's all.
Also, the reason being for the gradient, right? You want the gradient.
Yeah, the gradient is in the same shape as the input. The derivative is orthogonal to it, right? That's it. In our notation, you can change notations. You have to follow some standard, right? And so once you perform you're going to go through your training instances. Each training instance is first passed through the network. Then you pass it backward and compute all the derivatives. And then you aggregate the derivatives and average them. And the average derivative is what you're going to be using to update the network parameters. Now, you've already begun looking at your homework, so this is going to be fairly straightforward for you guys. Now, do you mind turning your phone off? That's you, the one who just looked at me, says, guiltily, turn your phone off. Please turn it upside down. Yes, I do not want to see it face up. If you want to look at Facebook, you're welcome to do so. Go outside, do so, complete your job, and come back in. Right? All right. So this is, okay. Now, the way we described it just now is where we computed each value one at a time, right? But you're never actually going to do that because it's highly inefficient. And for the longest time, we actually implemented deep neural networks in this manner, and it didn't work too well until we began getting GPUs, and we realized the value of vector formulation. So what is the vector formulation? I can restate the entire process in vector terms. First, think about this. If I have some previous layer neurons, right, then these are all the Ys that come out of the previous layer. I can arrange them as a vector with as many components as the number of neurons in the previous layer, right? Then I can define a weight matrix where each row is the set of weights to one of the neurons. So the first row here is the set of weights that come to the first neuron in the next layer. The second row is the set of weights to the second neuron in the next layer, and so on, right? And so now I can define a weights matrix. I can even define a bias vector where the vector is the vector of biases for all of the neurons in this layer. This notation making sense to all of you guys? Right. So once I write it in this manner, it's very simple. W times Y is going to give me Z. Why? Because if I write things in this manner, I have, these are all the weights of the incoming connections to the first neuron. Y is the set of output values from the previous layer. So if I look at this term times this, plus this term times this, plus this term times this, plus this term times this, is going to give me the Z value of the first neuron. And so the whole thing will just work out. And I can also add the B out here if I choose to represent my biases separately. So this equation holds, right? And so I can say Z equals WY plus B. Very trivial. And then subsequently, I can define my activation function, and I can apply my activation function on my Z, and I get the corresponding Y, right? So f of Z equals Y. Now, see the difference in notation between this and the previous scalar form. It is trivial. And so if I want to write the entire forward equation, I can just say Y0 equals X. I can say Z1 equals W1 Y0 plus V1. Y1 equals F1 of Z1. Z2 equals, W2 Y1 plus V2. Here now I'm using the subscript to represent the layer number rather than a superscript because I don't want to confuse it with squaring, right? And then apply the next activation and so on. And so this is a very easy way of thinking about things. And the vector formulation really simplifies the notation. But far more than the notation, you can actually use vector libraries, your GPUs, and so on, and make the coding, the code really, really efficient. And so here's what your entire forward pass is going to look like. That ugly piece of code we had earlier ends up becoming so simple. I'm going to initialize my Y0 as my input, and then I'm going to go through the layers, and then at each layer, I first compute my affine value, WY plus B, and then put it through an activation. That's it. Right? And then I'm done through with all the layers. My computation is done. Everyone with me so far? So what would be the challenge here? If I'm going to begin writing things in vector format, the challenge is how do I compute the derivatives going back? And how many of you are completely comfortable with vector derivatives? Raise your hands. Okay, nobody's lying, right? Because if I saw a hand raised, I know that there's someone here who's kind of overestimating their abilities. I didn't raise my hands, right? So, but it turns out it's not so hard. How many of you are familiar with the concept of a Jacobian? What is a Jacobian? So first, let me give you a couple of different things. So this is the forward pass, okay. Now, before presenting the backward pass, vector calculus, okay. Here, definitions. We saw that for any scalar y equals f of z, what was where z is a vector, what was the derivative rule? Anybody? You guys remember? What was the derivative rule? Tika, you tell me.
It's just like dy over dx.
Was it a dy over dx? What is the ratio? What was the derivative rule for scalar functions of vectors? We did this only 2 classes ago. Sam.
Get a vector.
Get a vector, right? So what would dx be? Would dx be a scalar or a vector? What is dy over dx? You guys remember? So what was the derivative rule here? Come on, guys. Give me a... Tony, you know the answer. Was it dz? Can I write dz over dx? I cannot, right? Z is the argument. Yes, Justin.
Y was a scalar, X was a column vector, and then we had delta Y, which is a row vector.
Delta y is going to be a scalar in this case, right? Guys, you guys are sleeping so much. It's there on the slide. Somebody wake up, look at the slide, right? When I ask you a question, the odds are I already put the answer up on the slide. I'm not asking you for the answer, I'm checking if you're awake. Okay, so we literally said delta y is the derivative of y with respect to z times delta z, and this is the only formula that works, right? Does everybody remember this? Raise your hands if you do. The act of raising your hands will wake you up. Please raise your hands, right? Thank you. So if z is a column vector, what is delta z? Delta z? I can add delta z to z, can I not? So what is the shape of delta z? The same as z. If z is a column vector, delta z is going to be a column vector. So what will the derivative be? What delta y, is delta y a scalar or a vector? Y is a scalar. Scalar. So if delta y is a scalar and delta z is a vector, what is the derivative? It's going to be, guys, okay. Can everybody please say together row vector? 1, 2, 3. Thank you. You guys have to wake up, right? So this thing is going to be a row vector. This is going to be a column vector. Everybody with me? Okay. So now this is your standard derivative, right? It's there. The next one, I'm not going to actually show you the slide first. This is this. Suppose I have y equals f of z, but y is a matrix also, a vector also, and z is a column vector. Then how could I write this? What would the derivative rule here be?
The derivative will have to be a matrix.
The same rule is still going to apply. I'm still going to say delta y equals the derivative of y with respect to z times delta z. That's the beauty of this notation, right? That I still use the same notation, nothing changed. Okay? But what is the shape of delta y? The same as y or different? What about delta z? Delta z, the same as z, right? So what is the derivative shape going to be? I have something multiplying a vector which gives me a vector. What is that something? It's going to be a matrix, correct? And so this one, if this is a n cross 1 vector, and if this is an n cross 1 vector also, this guy is going to be an n cross n matrix. So the shapes are easy enough, but then here is the cool thing. I can simply think of y1 through yn as n independent functions, scalars, right? What is the derivative of each of these scalars with respect to z? Is it a row or a column? Row. So what would the derivative of y, the entire vector with respect to z be?
Stack.
It's going to be a stacking. This is going to be, I can literally write this as delta y1 through delta yn is going to be a function of delta z1 through delta zn, and this is going to be a matrix, and each of these rows is the derivative of and so on. It's just a stacking. Did that make sense? Because y is a stacking of components. So the derivative of zy with respect to z is a stacking of derivatives. This matrix is called, it has a name. Anybody know the name? This is your Jacobian. Right? And so when I apply an activation function to a vector and get a vector, there's a Jacobian. Everybody with me? So that guy is a Jacobian. Okay. Now let's, which is going to be just a vector of matrix of partial derivatives, obviously, once I define it in this manner. So now let's take a special case. I have a special case where y is a vector, equals w times z is a vector. What is the Jacobian of y with respect to z? Here is how you think about it, right? Delta y is going to be something times delta z. What is this something? Why the question? Thank you. Right? Can everybody say W? Why? Because I can say y plus delta y is going to be w times z plus delta z. And we know these cancel out. So delta y equals w times delta z. So what is the derivative of y with respect to z? W. Easy, correct? And so if I have an activation function, this is going to be kind of, you have to compute the derivative. It's just a simple matrix transform. It's just the matrix itself. And now maybe, just maybe, you guys can give me this extra thing, right? If I have something of this kind, which is z1 influences y1 influences z2, just like so. What is the derivative of z1 with respect to z2? I'm drawing influences diagrams again. I'm no longer stating whether these are vectors or scalars. I'm stating something generic, right? If I state something generic, I can write this over here as the derivative of y1 with respect to z1. This is the derivative of z2 with respect to y2. Everybody with me? Okay. What is the derivative of z2 with respect to y2? Z1. Okay, so let's work this out, right? I'm going to say delta z2, z equals the derivative of z2 with respect to y1 times delta y1. Correct? Everybody with me? That's how the matrix operators work. I cannot change the order. Correct? And then delta y1 equals the derivative of y1 with respect to z1 times delta z1. Is everybody with me over here as well? Okay, so what is delta z2 in terms of delta z1? Product of what? I can plug this in here, right? This is, yeah, so this is going to be delta, this is delta, the derivative of z2 with respect to y1 times the derivative of y1 with respect to z1 times delta z1. Is this making sense?
Yes.
Everybody, is this making sense? Yes. Okay, what did I do? I just multiplied the derivatives. But in which order?
Backward.
Reverse order, because I worked my way backwards. That makes sense to everybody? So all I needed to do was to multiply this derivative with respect to this derivative, but this came out front. And so I can say Z1, Z2 is delta Z2 with respect to Y1 times, derivative of Z2 with respect to Y1 times the derivative of Y1 with respect to Z1. As I go from back to front, I'm going to keep multiplying things backwards. Everyone with me? Yes. Okay. So I've actually given you everything you need to compute backprop, believe it or not. Okay? I'm going to give you one more rule, which has to do with parameters. Let's say suppose I have something of this kind, where I have y1 going to z2, and the parameters are w and b, because z2 is w times y1 plus b. Let's just say that, right? Then does b influence z2? I can draw the influence diagram for b and z2, correct? Yes. So I have b influencing z2. So what is the derivative? And this is just 1, correct? So what is the derivative of z2 with respect to b? It's an identity matrix. What is the derivative of z2 with respect to w? This ends up being somewhat trickier. Okay, z2 is a vector. Y1 is a vector. If you work the whole thing out, you're going to get, and w is a matrix. The derivative of a vector with respect to a matrix is going to be what? A tensor. N times, so it gets to be very ugly. You can't really, you can work this out, but then here's where we use something very cool, which I'm not going to prove. I'm just going to give it to you, and then if you want the proof, we can work this in. Do you mind if I go 5 minutes over, guys? I want to finish this. Right. So let's say I finally go to a scalar L, right? If I'm trying to compute dl over dw, L is a scalar. What is the shape of dl over dw? Matrix. But what shape? W transpose, correct? So this is going to, and so let's say this is an n cross 1 vector. Let's say this is an m cross 1 vector, and this is a scalar. What is the derivative of L with respect to Z2? What is the shape? 1 cross m, correct? So the derivative of L with respect to Z2 is going to be 1 cross m. What is the derivative? And this is n cross 1, right? What you will find is the derivative of L with respect to W is going to be, so this would of course be m cross n, right? This derivative is going to be n cross m, and this is simply going to be y times the derivative of the loss with respect to Z2. You can check the shapes. You can work out the arithmetic, but this will always hold true. You guys with me? I said the derivative of z with respect to w is a tensor, but the derivative of L with respect to w, right? I'm saying z is eventually influencing a scalar L. That's going to be the shape, which is the shape of W transpose. So everybody with me? This bit of religious belief, dogma, you're going to have to believe it. But then if you believe it, there's just this one little extra bit. And then we're all set to do backprop. Okay? Everyone with me? Okay, if you got this, everybody say yes together, please. 1, 2, 3.
Yes.
And some of you didn't. So can we try this again or ask me why? 1, 2, 3. Yes. Thank you. Right. I have to do this because I know you guys are dopey, so am I, right? Please bear with me. These are antics that one has to follow. But now I have a whole bunch of slides talking about all of this, but I'm not going to go over the slides. I think you get the idea. Except for the case of activation functions, if I have scalar activation functions, the Jacobians are going to be, it's going to be a diagonal matrix. If it's a full vector activation function, you're going to get a full Jacobian matrix, right? And for the affine function, the Jacobian is simply the weight matrix, right? So now skip all of this. Actually, there's a poll. And then I'll take an extra 5 minutes and we'll be done with backprop. For this, you may have to carefully think about what influences what, think about it in terms of arrows, and then figure out which is the direction in which the products must work, right? This is important. Thumbs up, okay. So somebody on Zoom, can you answer? Which is the correct one?
The second option.
The second option, it's going, you have outward in, right? You start from the end, then you keep multiplying to the right. Beautiful. And so now we are all set to perform the backward pass. We are going to use this principle that our loss is eventually a scalar. So although these z's and y's and their derivatives with respect to w are hideous tensors, when you actually compute the derivative of the loss with respect to w, it collapses to this very simple product of vectors, outer product of vectors, which will be a matrix of the right size, and then we are set to go, right? I'm going to assume that I have the derivative of the divergence with respect to y, right? So if I want to, actually, you guys help me now. You have all the rules. So since we have 5 minutes to spare, you are going to help me with this derivative computation, right? I have the derivative of the divergence with respect to y. What is the derivative of the divergence with respect to z? Out here. The z just before the y. What would it be?
The derivative of z with respect to y times the derivative of y with divergence with respect to y with respect to z.
So where will it appear? To the left or right? To the right.
Right.
Yeah, you're going backwards. So this is going to be the derivative of y with respect to z. What is this? What is that? That's the Jacobian of the activation function, correct? And so I can just multiply that to the right. And now I have, which is the Jacobian. And so now I have the derivative of the divergence with respect to z. Everybody with me? Okay, now, so I have the derivative of the divergence with respect to z. What is the derivative of the divergence with respect to the previous y? Anyone?
What do you mean previous?
The y of the previous layer.
That you right multiply the weight matrix.
Right multiply with the derivative of z with respect to y. Correct? So this is going to be times the derivative of z with respect to y, and this is your weight matrix. Everybody with me? And so I can compute the derivative of z with respect to y, which is just the weight matrix. So easy, right? What is the one term missing? What is the derivative of the divergence with respect to the w? So again, to remind you, if I have, what we said was that if I have a y which influences through a w a z, which influences a scalar loss, then the derivative of the loss with respect to w was y times the derivative of the loss with respect to z. And we found that this shape worked, correct? Everybody remember this? You guys remember this? Right. So now what is the derivative of the loss over here with respect to that weight matrix W?
It's the y into the loss, derivative of the loss with respect to z.
Guys can say, okay, here's what I want everyone to say after me aloud because the class is almost over. It's going to be y times the derivative of the divergence with respect to z. Come on, say it. Okay, you won't forget this, right? Because you embarrassed yourself. This is going to be the derivative of the divergence with respect to w. Beautiful, right? And so now I have computed all the derivatives until here. I can take a step back. I can right multiply the derivative with respect to z by the Jacobian of this activation, which is now going to be a diagonal matrix. I get the derivative with respect to the previous z. I can right multiply that by the previous w. Always right multiplying, right? to get the derivative with respect to the previous z, and I can also compute the derivative of the weight by multiplying the y by the derivative of the divergence with respect to the z. So anytime you have a connection of this kind, y multiplied by w gives you z, then the derivative of the loss with respect to w is y times the derivative of the loss with respect to z. I can follow that. I can follow these principles all the way to the first layer of the network, and the equations were trivial, right? Something that looks so horribly complicated, when you actually work your way through the arithmetic in vector form, and if you just follow this, if you draw some simple influence diagrams and work out the logic and the order of computation, it all makes sense. Does it make sense to all of you? Raise your hands if it does. Thank you. Sorry to make you do that. So here's the backward recursion step. All I have to do is at each time, I keep right computing, right multiplying by Jacobians or weight matrices. And for computing the derivative for the weight matrix, I just multiply the input to the weight by the derivative for the output, right? And that's it. So there's some pseudocode over here. So if we're going to be setting up for digit recognition or something of that kind, I'm just going to be given data of this kind. I've defined my input data, where the class labels are either binary likely, if I'm performing binary classification, or multi-class, if I'm performing multi-class classification, in which case I'm going to convert it to one hot. And then for this, I'd have a softmax layer here. I'd just have a sigmoid. And then just use the simple backpropagation rules to compute the derivatives with respect to all network parameters and use them in gradient descent. So the story so far, neural networks must be trained to minimize the average divergence between the output of the network and the desired output over a set of training instances with respect to network parameters. Minimization is performed using gradient descent. And gradients can be computed using backpropagation, which requires a forward pass of inference followed by a backward pass of gradient computation, and the gradients can be incorporated into the gradient descent. So far so good, right? Was today's class clear enough for you, at least that you can go back and look at the slides and figure it out? Thank you, right? We're done. In the next class, we'll look at convergence. How well does it learn, and how we can improve, and how we can generalize, and what is the output we're looking for. Thank you all. Thanks for your patience.